Let me go through some examples with you directly, and you can look at those as a review. I think it helps to see them worked out a little bit better. So, how many moles of lithium sulfate should be formed when 5 moles of strontium sulfate react with 4 moles of lithium nitrate? I'm sorry, nitride. So, first of all, I'll suggest you pause the video and write the balanced equation yourself first in your reactants products. All right, so we have strontium sulfate, should be SrSO4, reacting with lithium nitride, so it should be Li. Hopefully you have Li3N. Of course, 2 ionic compounds, double displacement reaction, will produce Li2SO4 plus SR3, if I can write that. Be a little bit neater. SR3N2. So this should be 2 and 3. Should be right. All right, so I always like to separate out my calculations. I think it helps a lot to remind yourself what you're doing. So first thing I need to do is find my limiting reactant. Now, the first thing when looking at a problem with stoichiometry is to decide, is this a limiting reactant problem? Because earlier in the chapter we did a lot of problems that were not limiting reactants, or well, in a way they all were, but you were really told in some way or another which problem or which reactant was a limiting reactant. If I were to say how many moles of lithium sulfate in this case could 4.5 moles of lithium nitride produce, well, I'm telling you lithium nitride is my limiting reactant. I'm implying that I've got excess strontium sulfate, and that all that lithium nitride is going to be reacting. Or in many cases we're just given one component. So basically, if you're given both reactants, or 3 reactants if there are 3, in some cases, then you really have to figure out which one is going to be used up first. If you're only given one reactant, then in all likelihood that's not a limiting reactant problem, or not one you have to do any serious calculations with. So first is find the limiting reactant, and I always like to, didn't leave myself much room here, but put underneath my balanced equation the moles of each compound. So I've got 5.0 moles of strontium sulfate. Just to remind myself, sort of takes out of the paragraph, I've got 5 moles there. I've got, 4 moles of lithium nitride. So I want to take these and find out, what I'm really going to do first is say, if all of my strontium sulfate reacts, how much, let's say, how much strontium nitride is going to be produced. And then I want to say, well, if all my lithium nitride is reacting, again, how much of my strontium nitride can be formed, or what should be formed if it fully reacts. And this is how we determine which is the limiting reactant. Again, there's another main way that we can do this to find limiting reactants. I find that most students like this better. The other way I do it in my head more often, to be honest, but this is, I think, more successful for most students. So we really just do our basic stoichiometry. 5 moles of strontium sulfate, and use our mole ratio to moles of SR3N, and of course it's a 1:3 ratio, and 2 sig figs, that gives us 1.66 to 1.7 moles of strontium nitride. So that means if my 5 moles of strontium sulfate fully reacts, which is really saying that if my lithium nitride is in excess, I've got too much of it, the strontium sulfate fully reacts, that's how much strontium nitride I expect to be produced. And by the same token, 4 moles of lithium nitride, if this fully reacts, we'll do the mole ratios here. And of course this is a 2:1 ratio, which indicates this would produce, if it fully reacts, 2.0 moles of strontium nitride. So this means that we have a smaller amount of strontium nitride produced from our strontium sulfate. So strontium sulfate is our limiting reactant. So in this case, the 5 moles of strontium sulfate is the limiting reactant. People tend to think it makes up and try to say that our product is limiting reactant, but again, as the name implies, this is, and I often like to remind myself, I'll put it over here somewhere, just LR in circle, or maybe over here. Just to remind myself now, that is my limiting reactant. That's what I want to use for my calculations. So this is a theoretical process. Again, if I were to want to figure out how much strontium nitride is produced in this case, do not add these together, because these two reactants are reacting to produce the strontium nitride, so you can't add them together. So this is how much strontium nitride actually should be produced. But the question asks for strontium sulfate, and so I always like to separate out a new section. First, we're doing theoretical. We're trying to figure out which is our limiting reactant. Now we want to use our limiting reactant for all of our calculations. In this case, our basic calculation. Five moles of strontium sulfate. And now we're trying to get 2 moles of, the question asks, lithium sulfate, Li2. And of course, this is a 3:3 ratio, which makes it nice and easy. And so we expect to produce 5.0 moles of strontium sulfate. I'm sorry, lithium sulfate. Again, that's why it's always good to make sure to include your units. It's easy to get tripped up here, and this is just a great way to help you keep track of what you're doing. A little extra work, but it's well worth it. Just saves you lots of headaches, helps your grades, helps you understand what you're doing a lot better. When you go back and review what you try to go through your steps, and all you have are moles and moles, it's really, really hard to follow up what you did and what your reasoning was. So it's hard to correct or hard to try to troubleshoot any problems you might have. So including the complete unit, not just moles or grams, grams of something, moles of something, helps out quite a bit. And I also want to point out up top here, the limiting reactant in this case, look at, get the other pin out here. We started again with 5 moles of strontium sulfate and 4 moles of lithium nitride. A lot of people assume with that they want to skip the calculations and assume whatever we have the least amount of, that's the limiting reactant. Well, in this case, that's not true. Sometimes it is, sometimes not. We have more strontium sulfate, more moles of strontium sulfate, but that's the one that's used up first. And again, that's because of our molar ratios. Because we need 3 moles of strontium sulfate for every 2 moles of lithium nitride. So again, you've got to go through the steps. I'd always recommend break it into 2 steps. First, find your limiting reactant and label that section for your own sake, and then use the limiting reactant to figure out what your products are. So another problem, whenever we have 8 grams of hydrogen reacting with 32 grams of oxygen, what mass of water should be formed? So of course, write your balanced equation. And again, I always like to write down below here, I've got 8 grams, I've got 32 grams, and I'm trying to figure out my grams. I might put a question mark over there. But of course, our balanced equation only cares about moles. Now, some people might think, well, we're starting with grams, we're going to grams, why can't we just skip moles altogether? But you can't do that. There are some times where you might get lucky and the math works out, but in most cases it does not. So resist the urge to just skip moles altogether. We have to figure out how many moles we have. So 2 sig figs, I think 8 grams of hydrogen is still going to be 8 moles of hydrogen atoms. So actually 7.9. So 7.9 moles of hydrogen. Of course, this is going to be actually, I messed that up. I'm not even paying attention. Probably because of my sloppy handwriting up here. You're probably wondering what the heck I was doing. All right, so of course the molar mass of hydrogen, this is diatomic, is 2. I'm still doing I think, mentally thinking about mass percent from the last video. So anyway, 8 grams divided by 2.02 grams per mole gives us 3.96, or rounds out to 4.0 moles of hydrogen. Of course, this gives us, you work this out, 1.0 moles of oxygen. Hopefully you can work those out yourself at this point. So again, we always have to go through moles. And so we want to find our limiting reactant. So 4 moles of H2, moles of hydrogen, 2 moles of water. Of course, there's a 2-to-2 ratio. So if all the hydrogen reacts, we expect this to produce 4.0 moles of water. We have 1.0 moles of oxygen. And of course, a 2-to-1 ratio. Therefore, we expect this oxygen to produce 2.0 moles of hydrogen of water. And we want to know the total amount of water being produced. We're trying to find the mass of water, but of course we have to have moles of water first. So now we need to use our limiting reactant. And again, I stress, do not add these two together. That's not what this is showing us. This is showing us in each case, each calculation, if that component, if that reactant were to fully react, that's how much water would be formed. But remember from our balanced equation, if we react 2 moles of hydrogen with 1 mole of oxygen, we produce 2 moles of water. So they're combining, so we're looking at kind of at each half of that process down here. But they're combining to form the same molecules of water. So you can't add these together. Whichever one is the least amount produced, that's how much water will be produced if this reacts like we expect theoretically. Therefore, my oxygen is my limiting reactant. I'll put it down here. I might put it up here to remind myself. That's my limiting reactant. So that's the one I want to use for all of my calculations. And now we have really the same calculation we just did above. And now we need to convert that into mass. And this should be 18.02, puts 2 sig figs. I'll get 36 grams of water produced. Final answer. And that's all there is to it. Just make sure you have to go through moles first. You have to, you can't just skip, even though we're going from mass to mass. We're going through, mass of one compound to mass of another, so we have to go through moles in the interim. All right, so let's look at, after 3.5 moles of calcium nitrate reacts with 2.5 moles of sodium carbonate, how many moles of each reactant are left? So again, this is a good example of helping you understand what's really happening in a chemical reaction. So first thing is write your proper balanced equation. So I suggest you pause the video again and do that first, then come back here. So let's be at 3 there. Plus sodium carbonate, they react. Of course, this is a double displacement reaction. So we get calcium carbonate plus sodium nitrate. And I think we just need a 2 here, and that should do it. So we know we have 3.5 moles here, and we're starting with 2.5 moles here. So you may want to pause and work this out yourself first, then come back here. It makes you think about the problem a little bit more than the previous problems we've done. moles of, again, let's say calcium carbonate. And of course, this is a 1-to-1 ratio. So expect it to form, calcium carbonate. And then so of course we also expect to produce 2.5 moles of sodium carbonate. Calcium carbonate, sorry. If all of our sodium carbonate reacts. So of course, this is the least amount. So sodium carbonate is my limiting reactant. Might put it up here. Again, just to remind myself. And so that's what I use for all my calculations. Now, in finding my limiting reactant, I converted to moles of calcium carbonate. I could have gone to sodium nitrate, doesn't really matter, as long as both I'm comparing to the same product. So I could not have one calculating moles of calcium carbonate, the other calculating moles of sodium nitrate. Then I'm comparing apples and oranges. I've got to compare the same product to see which one is going to be used up first. So in this case, whichever, either one you pick will give you the same answer. So the sodium carbonate is consumed first, which we expect because we have a 1-to-1 stoichiometry between these. So in this case, the one you have the least amount of is the limiting reactant. And now we use our limiting reactant. So we're asking for how much of each reactant are left. So I'm going to take my 2.5 moles of sodium carbonate and figure out how many moles of calcium nitrate are going to be used up. One-to-one ratio. So of course, we expect to need 2.5 moles of CaNO3 Now, I want to point out again, it sounds obvious when we discuss it this way, but reactants versus products. Up here, calcium carbonate, this shows me that 3.5 moles of calcium carbonate is produced. Same thing, this tells me that 2.5 moles of carbonate, well, I say not is produced, I maybe say should be produced if all that reactant reacts. And again, here, 2.5 moles of calcium carbonate should be formed if all of my sodium carbonate reacts. When I'm looking at comparing products to the products, this is how much calcium nitrate is consumed. So that's used up. So the amount of calcium nitrate left will be your initial minus your consumed. So therefore, 1 mole of calcium nitrate is left. Again, the question asks for how much of each reactant is left, how much is unreacted in this case. So 2.5 moles of calcium nitrate reacts, so there's 1 mole left behind. And now, how do we do the same thing how do we do this for sodium carbonate? Well, by definition, the limiting reactant is one that's used up completely, so therefore, there's no sodium carbonate left. So 0 and 1 mole or how many of each of our reactants are left behind.